So let's start. So today I'm going to introduce this linear quadratic regulator model. So this is one of the most classic optimal control model that people study in theory. And then our TAs will actually switch topic and tell us a little bit about some of the simulators that we're going to use during the for programming part of the homework. Right. I just want to do a quick recap on the new model that we introduced at the end of last lecture. Right, so last lecture, we went through this new model very quickly, and some of you probably still, still trying to understand this model. So let's recap it together. So, so different from the infinite horizon Markov decision process that we have been talking about. So this new model has these two new quantities, right? So this capital H quantifies the number of steps in this particular task, and this mu0 is initial distribution. So the first state of this task is always sampled from this fixed distribution, right? And the rest of the stuff are the same, transition, probability, reward function, state and action space, right? And we argued that in this model, we have to consider time-dependent policies, right? Because, if you're facing the same state at a different time step, the optimal action that you're going to take might be different, right? Because if you're facing a particular state in the last time step, due to time limit, you only have one step to go. So your choice is probably taking, those myopic action that gives you some immediate reward, right? But if you at the very early stage, you might, the optimal strategy might be actually to ignore some of the myopic rewards, and so that later on you can go for a larger total reward in the end, right? And then the way that this time-dependent policy interacting with the Markov decision process is as follows, right? So we always just start from S0, sampled from this fixed initial state distribution. And then at time step X, we just take action based on the policy pi H that is defined for that particular time step, right? And the rest of the stuff is the same. You sample a state from the transition and you get a reward for that state action pair. And then you only repeat for H-1 steps. Sorry, there's this typo here. I will fix this afterwards. Right, so the reason that we said this is H many steps because we take H many actions, right? We do A0 from A up to H-1, right? And the reason that we start from 0 rather than 1 is that, as a computer scientist, we always start from 0, right? All right, so then the value function are basically the same, except nowadays we also index it by time step H, right? So in words, this basically says that if I start at time step H at state S, and then I follow this time-dependent policy, right? For the rest of the steps, what's the expected total reward that I would get, right? So one thing that I want to emphasize here is that we do not have any discount factor, right? So this is just a straight sum over time steps. And remember that action at time step tau is actually taken by the policy indexed by tau, right? So let me write out this. So during the semester, we're going to often use this notation for finite horizon Markov decision process. Right, same for Q function. You take at time step H at state S, you take action A first, and now you switch to policy pi for the rest of the time steps. Right, and then we have a basically very similar Bellman equation, except now we don't have this discount factor anymore here, right? Because we don't care about discounting. We just want a straight sum over this finite number of steps. And people do consider discounted setting as well here in this finite horizon setting. If you really care about discounting the future outcome, okay? But one thing you could do is that you just absorb this this discount factor into the reward function and make a reward function also time dependent, right? And then this model still captures the finite horizon MTP. All right, but we're not going to consider discounted setting finite horizon MTP, right? And another common, so now we have introduced two models, right? Infinite horizon discount Markov decision process and this finite horizon Markov decision process. So in the literature, there is another model, which is infinite horizon average setting, which is not as popular as these two that we are talking about. So in this lecture, in this semester, we're not going to talk about the third model, right? But you can, if you're interested, you can maybe find out in the book that we are writing, right? But it's not as popular as these two models that we use. All right, so we quickly went through the dynamic programming process, all right? But maybe let's slow down a little bit and look at an example in terms of how to compute in the optimal policy. All right, so here let's just consider a very simple Markov decision process. That is a grid word. We have reward 1 here. Right, so this is a simple Markov decision process, and we have 5 actions. We can go up, left, right, down, and stay. Right, and the transition is deterministic, and if you bump into a wall, you're gonna stay in the same cell, right? So if you're somewhere here and you decide to go right because you bumped into a wall, so you're gonna stay in the same cell. So that's how the transition is defined. Right, so the reward function here is defined such that R of state 2 and 4, right? So state 2 and 4 means that this is the cell that corresponds to row 2 and column 4. Okay. Oops. Action A equals to 1 for all A, and RSA equals to 0 otherwise. Right, so if you add this cell indexed by 2 and 4, then no matter what action you take, you're gonna get reward 1, right? So imagine this is a state that has some gold. So you go, if you enter into that cell, you get the gold 1, okay? And no matter what action you take, and the rest, basically reward is 0. And so this is kind of weird to reward function. Basically, this reward function is saying that our reward function only depends on state, right? Like it has nothing to do with actions. In other words, we can just write RS equals to RSA for OA, right? Because conditional and conditional on a state S, no matter what action you take in this model, your reward is basically the same. Right. So let's just use this example to show how we can actually compute the optimal policy and the optimal value functions. Right. So as usual, we're going to start from the last time step. So capital H minus 1. And we convinced ourselves that Q star H minus 1 SA is just RSA. Right? Because if you, at the last time step, you only have one choice, right? One more step to go. And the Q function is basically the reward function, right? Because if you take this action, you terminate this episode. And this one step immediate reward is your, total future outcome. Right? So now basically by definition of V star, max over A, RSA, which by our assumption here is just RS, right? Because again, in this reward function setup, the reward has nothing to do with action, right? No matter what action you take at this state, they're the same. Right, so now this table is very simple, right? So let's just write out this table, VH minus 1. Oh, by the way, this shaded cell is think about this as obstacle, right? So if you take action right, bump into this obstacle, you're going to stay at the same cell. Right, so we argue that V star H minus 1S is basically the reward function. So we get 1 here, 0, 0, 0, 0, everywhere. Right, so this is our table at time step H minus 1, the last time step. And now let's see how we're gonna, so now we have this lookup table. Okay, so this is a table that we already computed. Now let's see how we can use this lookup table to compute a table at capital H minus 2. All right, so now at H minus 2. So let's see, I want to compute, let's see, I want to compute the value. Let's see, we focus on cell 3 and 4. Okay, so 1, 2, 3. Okay, so let's see, let's focus on computing the value for cell 3, 4, which is the bottom right cell. Right, so Q star capital H minus 2, 3, 4. Let's see if we take action up. Right, so we care about the value at cell 3, 4, which is the bottom right corner. And we also try an action that goes up at this time step, right? So by the transition operator, we know that if we take action up at this particular cell, at time step capital H minus 1, we're going to reach the cell, which is 2 indexed by 2 and 4, right? So this is equal to reward 0, because at this particular state, 3 and 4, we don't get any reward, right? Because we only get reward at the cell that is indexed by 2 and 4. And we know that by taking action going up, at the next time step, we reach the cell which that actually contains a reward, right? So we get V star capital H minus 1 indexed by 2 and 4. Right, so now we can actually just copy the value from the previous lookup table, right? So now we can actually go to the previous table that we just stored, right? And search for this value and copy it here. Right, and we can do the same process for the other actions as well. Q star H minus 2. So let's do the action that actually just do nothing. So remember, we have an action that can actually just stay at the same cell, right? So this is again 0 plus V star H minus 1 of the same cell, right? And again, we just go to the previous table that we computed, right? And look for this value and copy it here. Right. Once we have done this process for every action, we can just use the definition that V star H minus 2, 3, 4 is just max over, all these Q values at each of the action. Right. So the basic process is that we compute some lookup table, right, at this particular time step, and now we move to the previous time step, and now we use the lookup table that we just computed to compute the current lookup table. Right, so this is exactly how dynamic programming actually works. Right, so now of course we can formalize this problem. Right, so this is basically what we did. So we started from capital H minus 1, right, and we argued that Q star capital H minus 1 is just equal to the reward function. Right, because this is the last time step. There's no sort of long-term effect you can reason about, right? You take one action, you're done. And the optimal policy, of course, is just a very myopic policy, right? Just focus on the current reward function and optimize the reward function. And then we compute this guy. Oh, typo here. So this is our lookup table, right? Which we're going to use to compute the lookup table at time step capital H minus 2. right? So this is basically the dynamic programming process. Right? Any questions so far for this dynamic programming process? So you should try to convince yourself, just by this construction, by this dynamic programming algorithm, right? So the function, the policy you computed is actually the optimal policy, right? So like, let's first argue why this policy is the optimal policy, right? Because this is just the last time step. There's no better policy that I can do other than just picking the action that achieves the maximum reward, right? So now let's do induction, right? So imagine that I've already computed V star H plus 1, and let's use inductive hypothesis that, starting from H plus 1, I know how to behave optimally, right? So now we should convince ourselves that this policy is the optimal policy at this time step, at the current time step, right? Because at this current time step, I'm trying out all the actions, right? I'm trying out all the actions. And once I try this action, I follow the optimal policy, right? By inductive hypothesis, I've already computed the optimal policy afterwards. So this should be the best policy, because otherwise, you're basically saying that starting from H plus 1, there might be a better policy, but that contradicts our inductive hypothesis, right? So it's like, I'm going to stay here. I have 3 actions to try, right? And by inductive hypothesis, I know that after I tried any action, I know the shortest path to get to this goal, right? So now I just needed to evaluate the length of 3 trajectories and pick the one that has the shortest length, right? That should gives me the shortest path, because otherwise you're basically claiming that your inductive hypothesis does not hold, right? So unlike value iteration and policy iteration that we looked for infinite horizon discounted setting, here we don't need to do any sort of iterative analysis, right? So by construction of dynamic programming, this gives us the optimal solution, right? And this also just proves that this deterministic state-dependent policy is actually the optimal policy for this finite horizon Markov decision process. Okay, any questions so far?
Professor?
Yeah.
This only works when we have an finite state and action set, right? Like,
not really, right?
As in, like, the algorithm would work, but like computationally, for example, to figure it out, it wouldn't work, right?
Yeah. So I think most of the case you're correct, except this linear quadratic LQR, this linear quadratic regulator model that we're going to look into today. Okay. Yeah. So again, let me repeat this question. So computation-wise, that seems crazy, right? But information theoretically, or if you have infinite computation power, you can actually do this process, right? And this process gives you the optimal policy. And depends on the formulation for transition operator and reward function. For some special cases, we will actually be able to compute the exact optimal policy. Yeah, so I think this is a good time, for us to recap on the state action distribution, right? We can define the same quantity as we did for the infinite horizon discounted setting. So the first quantity is basically the same quantity that we had, right? So this is basically saying that this is the probability of reaching a particular state action pair SA following policy pi at time step h. Sorry, let me rephrase it. So the probability of reaching SA at time step h following policy pi from the initial state distribution mu0. Right, and we can define the average state action distribution now by just define this average, that straight average, right? Not exponential averaging anymore. So we have in total capital H many distributions. So our state action distribution is basically a straight average of them. Okay, so no discount factor anymore. And again, we can write our expected total reward just using this average state action distribution. Right, so this is very similar to the homework problem that you're doing right now. But again, we don't need a discount factor anymore because by our definition, the value function, Q function, we don't do any discount anymore, right? So everything is a straight sum over time steps. Right, so that's basically the recap. And now we're going to move to the optimal control side. Okay, let me actually pause a second here. Any questions so far?
Sorry, do you mind just going over what d pi is again?
This one? Is it this one?
Yeah, sorry. Yeah.
Yeah, so this is just by definition, the right-hand side of this equation.
Oh, okay. We're just defining it.
Yeah. Okay, let me use this notation. So this notation is A equal to B. So this is basically saying, by definition, A is equal to B. Okay, by definition, A is said to be something.
Thank you.
Okay, so now we're going to move on optimal control. So this is particularly relevant for robotics applications, right? Because in robotics applications, everything is continuous, right? We don't have discreteness anymore. So my state space is continuous in probably RD, and my action space is also continuous in RK, where D and K are some dimensions, right? So we're gonna move actually to continuous state and action space from now on. And let's look at a particular example, this catapult, okay? And so here in this setup, we have a pole and we have a cart, right? So the pole and the cart, they are connected by this joint, but this is an inactive joint in a sense that you cannot apply any force, any torque on this joint, right? And you can apply force on the cart. You can move the cart left and move the cart right, right? You can push it and you can pull it. And your goal is to actually balance in this port, right? So this is actually not a super easy task, right? So if you have a pencil or a pen, you can actually try it out, right? Like I can try to balance it by just moving my hand around, right? But this is actually not super easy, right? But in the homework problem, we will actually see how we can actually compute the optimal policy by just moving the cart around left and right so that the port is balanced. Okay, and we can see that we can formulate this problem as a Markov decision process, a bit that we have to deal with continuous state and a continuous action. All right, so this is, oh shoot, okay. Because I turned this into a PDF, so this is not a video anymore, but I think our TA will show you some animation. So this is the environment that you're gonna play around for homework, right? And you will see that you computed some policy and hopefully your policy can, balancing the port, right? By just moving the cart left and right. All right, so our goal is to stabilizing it around some point, right? So let's see, this is the goal. And let's use X star as the goal. So here, okay, so let me emphasize this point. So here I'm switching notations from S to X and A to U. Okay, so in control, we use X to denote state and we use U to denote action. Okay, so this is kind of annoying, but that's how these two fields actually work. And if you're wondering why they're so disconnected, I'm wondering the same thing. Right? So that's just how these two fields works. Yeah, so when we talk about control, we will use notation X and a U. Okay, and when we switch to Markov decision process later on, we will switch back to SA, right? Okay, so the reason that I choose to do XU is because it might be easier for you later on to read the control papers in case you decide to do research on control, right? Okay, so we can design this cost function, right? That actually balancing my pole. So this is my goal. So I want to penalize the distance to the goal, right? So this is a positive definite matrix. And this is also a positive definite matrix. All right. Oh, let me emphasize. So here, the state is probably let me call it y-axis. So the state is the position of the cart, the velocity of the cart, and the theta, the angle between the pole and the vertical line, and the angular velocity. Okay, so we have a 4-dimension state space. And as you can see now, the state space is actually literally continuous, right? Like it's like we at this moment, at least, we're not discretizing it. So that's the cost function that I designed for this particular environment, right? I'm trying to penalize my deviation to the goal state x star. And simultaneously, I'm also penalize the action control input, right? So I don't want to apply too big action. And the optimal control problem is basically the same as the reinforcement problem, right? So here we are again interested in minimizing, optimizing the expected total cost. So here I'm using the mean because now we switch language from maximizing reward to minimizing cost. Right? Again, this is another difference between RL and control. In control, people likes to talk about minimizing cost. Okay, so we're gonna use the terminology cost as well. But you really should think about cost, as very similar to reward, right? You can set cost to be negative of the reward, set reward to be the negative of cost. Right? So again, our goal is to optimize this objective function, which is the expected total cost along H many steps. And our goal is to find a policy that maps from state to control, state to action, right? And subject to my transition dynamics. So here, we're going to just focus on deterministic transition dynamics. For instance, for this environment in the homework, we're also going to look at this deterministic transition. So in other words, if I'm at this state S, if I apply that amount of force, what's the next state of my system? Right? Someone asked that can Q and R be semi-definite? They can. And it really depends on, it's basically you're the designer of the cost function, right? If you believe that there's some dimension that doesn't really matter, you can just set that, you don't have to penalize that dimension, okay? But in most of the case, we're not gonna set these two matrices to be, the matrix that has negative eigenvalues, for instance. Okay, but that basically means that you're encouraging, either deviating deviating really further away from the goal state, or you're encouraging, taking huge actions, right? That's usually not what we want to do in the control. Right, so that's the model of optimal control. So we optimize the expected total cost subject to our constraint that is used to define it. That is basically the transition dynamics. Okay. And sorry, here, let me add one more, ut equals to pi h. And our initial state is again sampled from the initial state distribution. All right, so for those of you who know physics better than me, you can probably figure out, what is the fxu for this particular model. Right? I mean, at some point, I think I know how to do it, but now I don't think I remember any physics. So, all right. So more generally, we can formulate this optimal control problem as follows. So we always start from a dynamical system, right? So this is a dynamical system that takes the current state and the current control as input, and also possibly takes some disturbance. Okay, so this is disturbance, and then map it to the next state. Right, so this disturbance could be the noise in your actuators, for instance, right? It also could be some constant, disturbance. And a lot of times in practice, we often assume that this disturbance is sampled from some Gaussian distribution, for instance. Right, so this is actually in practice a valid assumption, because by law of large number, we know that if you have many uncertain sources, if you average them together, the uncertainty kind converge to a Gaussian distribution, right? So that's why, in practice, people use Gaussian noise a lot. Right, and the objective function is to find the optimal control policy pi that minimizes this long-term total cost. Right, so here you might notice slight difference. I'm also actually penalize this additional state x capital H. So this is often used in control because people actually imagine that you are trying to drive the car to a specific goal, right, for capital H many steps. So you really want to design a huge penalty for the last state, right? Because if your car hasn't get to that goal, you probably should penalize it a lot, right? So we often design an additional cost function for the last time step state. But again, this is a H time step control problem because we only take H many actions. Right? We still do U0, U1, all the way to U capital H minus. So this is really a design choice, right? So you don't have to do that, but people often do that to penalize the cost for the last state in the trajectory. Yeah, so as I mentioned, this disturbance could be Gaussian noise, it could be deterministic, right? A lot of times in a lot of robotics applications, we often see that if you use that robot manipulator many times, it often have this constant deviation, right? Like if you command this arm to move to XYZ position, it often moves to this XYZ plus delta position, right? And if you repeat that same process again, it also moves to, if you ask it to move to X prime, Y prime, Z prime, it also just moves to X, Y prime, X prime, Y prime, Z prime plus delta, right? In other words, if you command the robot to go to some particular position, it often, instead of going to that specific position, it often goes to that position plus some deviation delta. And that delta is usually a constant, right? That happens a lot. And usually you have to recalibrate the robot, after you're using it for instance, several days. Right, so now as we see, right, we are dealing with continuous control and continuous state space, right? Think about the carpool example. This is a 4D continuous control problem, right? So now we may wonder, we spend so much time on this discrete Markov decision process, right? Maybe we can reduce this continuous control problem to discrete Markov decision process. So indeed we can, right? So the simple way to do that is just do discretization. So for instance, if my X space is 2D, right? So what you can do is just discretize it. And I label it 1, 2, 3, 4, 5. Okay, 4, 5. Let's say I discretize it with some fixed, accuracy epsilon. This is epsilon. This is epsilon, right? So now I can just basically reduce this 2D problem into a Markov decision process that contains 25 states, right? And I can actually start writing down the transition probability. Like what's the probability of transit from this state to that state by taking particular action. And similarly, I can discretize the action space as well, right? Once we are done with discretization, we can start writing down the probability transition P and reward function R. Right, we can do that. And if your problem is actually low dimension, people actually do that. Right, so if your problem is truly like 2D or 3D, you can actually do that. But this is often called curse of dimensionality, right? When the dimension actually increases, the number of points on your grid, on your discretized grid, basically approximately increase exponentially, right? So imagine you want an epsilon discretization accuracy, right? So if you're discretizing a d-dimensional box, the total number of points is basically 1 over epsilon to the d, right? So this is often called a curse of dimensionality. So you can imagine that if you're controlling a problem that has 10-dimension state space and 10-dimension action space, then this discretization method is not really going to work that well. Right? Remember that the algorithm that we talked about, such as policy evaluation, it takes roughly like OS squared, right? So now your number of states is going to be exponentially large with respect to your dimension. Right, so this is no good because we can do it for low dimension problems, but once we get to dimension like 10 or 20, it quickly becomes untractable. Right, so today we're going to look at this particular model, linear quadratic regulator. So this is one of the most popular model that people study in control literature, right? So we will see why. So this model is very simple, right? So now I'm going to make strong assumptions on the cost functions and a very strong assumption on the transition dynamics. So let's look at the cost function now. So my cost function is quadratic. Okay, and my cost function is quadratic in both state and in action. Right. So think about the problem as you're trying to control the robot to move to a goal position, which is indexed by 0. Right. You're trying to move to the center of the state space. So you penalize the deviation from the robot's current state to the goal, which is the 0 vector. Right, so our cost function is very simple, quadratic. We are quadratically penalize the deviation to the goal, and we are quadratic penalizing the control inputs. Right, we want to get to the goal, but we don't want to pay that much, cost on the control inputs. And the dynamics is also very simple. So it is a linear dynamical system. So given where I am and what control input that I do, the relationship between the inputs and the outputs are basically linear. It's linearly related to the output in terms of this A matrix and a B matrix. And my control is computed by the control policy that I'm trying to optimize. And here we're just going to assume that this disturbance is coming from this now Gaussian distribution, which has 0 mean and covariance sigma times identity. All right, let's just fix some notations for dimension. So my state is coming from this RD space, and my actions from RK space. So which means that my matrix A will be from R of D times D, right? And my B will be from D times K. And again, my WH is from R to the D. And my Q is from R D times D. My R is from R K times K. Okay. So let me emphasize both Q and R. They are positive, definite. Right, so that's the problem. So we want to minimize the expected total quadratic cost subject to a linear constraint. Right, so this model is often studied in theory, but less relevant in practice. So the reason that I put a question mark is that we're never really going to directly model a control system using this linear equation, right? Because it is unlikely true that this time homogeneous globally linear model is actually a globally accurate approximation of my dynamics, right? Even the simple catapult example that we see, the f function is not linear, right? It's really hard for us to find a global linear model that can actually approximate a nonlinear model everywhere, right? But as we will see in next week, this linear quadratic regulator often builds as an approximation oracle that we can use to compute local optimal solutions for nonlinear control problem. Right? So one thing that we will do in homework is also basically taking a nonlinear dynamic system. We're just going to linearize it along some waypoints, right? So we locally approximate nonlinear models using linear models, right? We do first order Taylor expansion, for instance. And then we just use LQR to compute the optimal solution. And then we repeat the process. Right, we will talk about this in next week. And the reason people love this model in theory, because you can actually derive the optimal control in closed form solution for this problem, right? So this, in hindsight, this is actually not surprising, but if this is the first time you see this problem, this is actually pretty remarkable. Like we are doing continuous control problem here, right? And we have noise, we have Gaussian noise here. And I'm claiming that here you can actually solve this problem exactly, and you can actually write down the optimal policy in closed form solution. Like you don't need to run like value iteration or whatever, hoping to convergence. We're just gonna derive the optimal policy closed form solution for this problem. Right, so let's look at one example. So this is, for instance, maybe a 1D vehicle movement problem. So I have a car here, I'm trying to move somewhere, right? So my state is the position and the velocity. Right, so V is actually just the time derivative of my position, right? Okay, so my control is this 1D force. And I also have to make the problem a little bit realistic. I have some friction that is, negative proportional to my current velocity. And my vehicle has a mass m. Right, so let's consider discrete time, which is 0, 2 delta, 3 delta, and so on and so forth. Right, so think about this is h equal to 0. This is h equal to 1. Apparently, I missed 1 delta here. H equal to 1. Equal to 2, h equal to 3, so on and so forth, right? So we are discretizing the time into constant time steps, constant time intervals, right? We're not dealing with continuous control problem in this whole semester. We only care about discretize. We only care about discretized time. Okay, so that's why we discretize the continuous time into constant intervals. And think about this, delta is tiny. All right, so we can apply, the basics of physics, the Newton's rules, to derive some approximation, right? So this is my car's mass. This is my acceleration, right? So when delta is small, this is approximately equals to the time derivative of my velocity, which is my acceleration, right? So we know that, F equal to ma, this is something that I still remember from high school. And this is F, right? Because this is my control input minus the friction, right? This is F equal to ma. And this is just, and this is just saying that I'm computing the time derivative of my position, right? Which is velocity. So if my time interval delta is tiny, then these two equations kind of holds. Right, and we can rearrange in terms. So now we have VH plus 1 equals to delta over m u minus eta times VH plus VH. Right, and we have PH plus 1 equals to delta VH plus PH. Right, as you can see now, the relationship between the state at time step h plus 1 and the state at time step h, the relationship is linear, right? And the relationship between the state at time step h plus 1 and the control input u that we added is also linear. Right? So we can write this as VH plus 1, PH plus 1 equals to some matrix times VH, PH plus some vector times u. Right? Let's fill in, these cells in this matrix. So if we do some calculation, we can see that VH plus 1 using this formulation. So we can see that this is 1 minus delta m times eta and 0 and delta and 1. Okay, hopefully I'm doing correct. And for u, we have delta over m, and we have 0. Okay, I think this is correct. So this is my A matrix. This is my B matrix. Right, so this is a very simple example of this linear quadratic regulator. But as you can see here, along, we are already using approximation, right? So these are approximation. So this is just give you a sense of, how we can actually, formulate a linear system using some approximation. Right, and same value function and Q function, except now we can just write the cost function in this quadratic form, right? Other than that, they're basically the same. Right, and we can define the optimal value function at time step h as the, the maximum possible total expected, the minimum possible total. Sorry, that should be mean because we're dealing with cost. So the optimal cost function, the optimal v function, is the minimum possible total expected reward that you could get if you behave optimally starting from time step h, right? So I'm doing mean over all the rest of the policies, right? So this is like starting from the state at time step h, do your best, compute the minimum total expected cost afterwards, right? So this is the definition of the V star. And a nice theorem tells us that in this problem, V star is actually a quadratic function. So in other words, you can actually write V star using this quadratic formulation. So here, PH is a matrix, is again a positive definite matrix, R d times d, and this is just a scalar. Right? And even nicer, we can write the optimal policy as a linear function with. So here, k star h is from rk times d. All right. And p and k, they can actually be computed exactly. All right. So that's one of the reasons that people love doing this model, because this actually gives you an optimal solution. Right. So in terms of how to derive it, we will do it together next Tuesday. Okay. All right. So that's basically the end of today's lecture. I mean, the end of the things that I want to talk about. So we introduced this LQR model, right? And it's a very simple model. It's you can argue that this is a very naive model, right? Because nothing, there's not that many things in the world are globally linear, right? But this is a nice model. It is a nice starting point for us to start optimal control, right? Because this actually allows us to compute the optimal control policy in closed form. As you already saw, the optimal policy will be linear in state, and the optimal value function will be quadratic. And we can actually write out this, in closed form solution. And later on, we will see actually how we can use LQR as building blocks to do approximate optimal control. Right? It's like, in machine learning, we always try to understand linear regression first, and then later on, we use probably can use linear regression for other stuff, for more complicated stuff, right? So here again, this linear LQR model is like a linear regression in machine learning, right? We need to understand linear stuff first before we can move on to nonlinear stuff. All right, so any questions so far? If not, I will ask the TA